going to see about that energy relation during braking. See, when we apply the braking, what is the relations between that energy? That's we will discuss over here. It has been noted that the most common brakes employ friction to transfer the brake system's mechanical energy irreversibly into heat, which is then transferred to the surrounding environment. The kinetic energy is absorbed during slippage of either clutch or brake. See, for the kinetic energy is absorbed when it is that slippage of that clutch or brake, and this energy appears as a heat. The main thing is here the energy is appeared as a heat. Then this heat, if the heat is faster than the dissipated, then the temperature rise. This we know already. If any heated is generated faster than that it's dissipated, then the temperature rises. Through a design of brake, therefore, requires the detailed transient thermal analysis of the interplay between heat generated by friction as well as heat transferred through the lining and the surrounding the metal to the environment, and the instantaneous temperature of this surface of the drum as well as the lining, then we will get that energy relation. For a given size of brake, there is a limit to the mechanical power that can be transferred into heat and dissipate without temperatures reaching the value. Then it is damaging levels which will not reaching there. See, if a given size of brake, there is a limit to that mechanical power that can be transferred into heat and dissipated without the temperature reaching the damage level, the motoring reaching the damage level. Then the temperature of the lining is more critical and the brake size is characterized by lining contact area A. Then heat generated in braking during the deceleration, the system is subjected to an essentially constant torque T exerted by the brake, and in the usual situation this constancy implies a constant deceleration too. Then the application of the work or energy principle to the system enables the torque exerted by the braking and work done by the brake, and we calculated from U equal to del E equal to d del theta. This is the formula. Then where del E is the loss of system total energy which is absorbed by the brake during the deceleration, transformed into heat and eventually dissipated. Then the elementary equation of constant rotational deceleration apply. Thus the brake drum is brought to rest from the initial speed W0. Deceleration and W naught to the power of 2 by 2, which is del theta equal to omega m into del t, which is omega m equal to omega m divided by 2. So del theta divided by del T, where omega m is the mean drum speed over the deceleration period. Then the mean of rate of power transmission by the brake over the braking period will called as Pm equal to U by del T, which is equal to T omega m, which forms a basis for the selection or the design of the necessary brake. Then the dynamics during the braking. Dynamics is the use of the electric traction motor of a railroad vehicles as generators when slowing the locomotive. It is termed heuristic if generator electrical power is dissipated as a heat in brake grid resistors, and regenerative if the power is returned to supply line. See, dynamic braking is lower the wear of friction based braking. The components, and additionally regeneration can also lower energy consumption. Dynamic braking is lower the wear of friction based braking in the components, and additionally regeneration can also lower the energy consumption. This is the main thing here, the lower energy consumption also. Then the dynamic braking can also be used on rail cars with multiple units, light rail vehicles, trams, and PCC street cars also. When braking, the motor fields are connected across either the main transmission generator, which is a diesel electric locomotive, or a supply electric locomotive, and the motor armature are connected across either the brake grids or supply line. Then the rolling locomotive wheels turn the motor armatures, and if the motor fields are now excited, the motor will act as a generator. During dynamic braking, the transient motors, which are now acting as generators, then are connected to the braking grids, which is large resistors. These will having the large resistor which put a large load on the electrical circuit. When the generator circuit is loaded down with the resistance, it causes the generators slow their rotation, which is MPH. By varying this amount of excitation in the transaction motor field and the amount of resistance imposed on the circuit the resistor gets, then the transaction motor can be slowed a virtual stop, which is approximately 3 to 5 mph. For that permanent magnet motors, dynamic braking is easily achieved, which is by shorting the motor terminals, thus bringing the motor to fast absorbed stop. This method, however, dissipates all energy as a heat in the motor itself, and so cannot be used in anything other than low power intermediate applications due to cooling limitations. It is not as suitable for transient applications also. See, the main thing is this method dissipates all the energy as a heat. The all energy will dissipate as a heat in motor itself. In that motor itself, it is dissipated as a heat, and so cannot use in anything other than low power intermediate applications due to cooling limitations. Then it is not suitable for transition application also. Thank you.